Thank you very much. Afternoon from Dalkennock in the UK. Good Lord, that's the first time we've had that in our chat window, I believe. But yeah, so Fred and I were just talking about, Carl Carlson, possibly the world's leading, the foremost expert. We've got someone from the Netherlands as well. Cool. The world's most leading expert on FMEAs as well. His colleague of ours, friend of ours. We do lots of podcasts together. But and he can, Carl can take you through there's as many differences between design and processes for me as much as anybody in the world. But what I want to talk today about is that what is the more or less philosophical difference between design and process for me is, of course, people who have been involved with FMEAs in the past will know about will know all about FMEA worksheets and scales and severities and things like that. But what is it that is the fundamentally what fundamentally differentiates one from the other? So what I'm going to start with is, for those of you who are familiar with my work, you'll recognize my good old smart lock. And the reason why I'm talking about the smart lock is because I want to talk about what a design FMEA is supposed to do. So a smart lock like this, which we designed from scratch, we know is going to have roughly 16 or 17 different components before we even think about designing it. And because we know this, we should be able to do a really robust FMEA, and hopefully that FMEA, or design FMEA, I should say, and that design FMEA would, for example, look at the design as it applies to things like door slams. The door that this lock is attached to is slammed shut due to wind or arguments or children, what have you. The idea of a design FMEA is to, as early as possible, come up with wonderfully simple, I call them fast, simple, free corrective actions like this one, where we use thicker gauge wire to provide more contact area with the motor terminal. We use shorter wire to accumulate less momentum when the door is being slammed. We include wire clips to physically secure the wire. And in the top, we now have socket and plugs instead of solder joints in the circuit board, which also makes it much easier to assemble. Now, these corrective actions, I hope you'll agree, are fast, simple, and free. And when I say free, of course, they're not entirely free. There is some cost associated with thicker gauge wires and the rest. But in practice, when you compare this to the overall recommended retail price or cost to put this thing together, these are negligibly cheap changes to the design itself. And of course, these changes might solve all sorts of crises and fires that you would otherwise have to deal with during production if you thought of them early. So design FMEAs are all about making reliability happen through design changes. We implement really early in our design process. And so the outputs of design FMEAs, no matter what anybody else tells you, is a list of prioritized corrective actions. Some people do FMEAs just to analyze a risk, which is to identify the most likely way your thing is going to fail, and then stops right there. And that's what we call admiring a problem and not fixing it. Every single document that pretends to be a standard or a textbook or a guidebook as it pertains to a FMEA, they all talk about how everything revolves around corrective actions. We're not here to admire a problem, we're here to fix problems. And so we want these really fast, simple, free corrective actions embedded in our design at the very, very start. So that starts our conversation on what a design FMEA is. And of course, there's more than just design and process FMEAs, and we'll get into that right now, starting with the sort of quintessential or baseline or basic life cycle or development life cycle, or whatever you want to call the way your organization comes up with a great idea for something and then starts to works out how to make it and then send it, or sell it, I should say, to customers. Now, you can see here on this very basic list of steps, we have an idea followed by a concept, which we try and flesh out that idea. Specifications, where we turn that concept into measurable things that designers and technicians and engineers and manufacturers can use to work out what they need to come up with. Then we have the design phase, where we actually work out, we put these things together. And of course, the design and the build phases are iterative. We're going to go back and forth as we go through different ideas. And after that, we're going to sustain our thing and we're going to dispose of it one way or another. And disposal for a commercial product might not involve any sort of actual accumulation of waste product. But a lot of organizations tend to overlook that by the end of the life cycle of a commercial product, we have a lot of really useful information for whatever it is we're going to do next. So the dispose phase, no matter what you do or you think you do, is very important to make sure, if nothing else, you learn as many lessons as possible. Now, some of us might have heard of a system FMEA. Now, a system FMEA is a FMEA which is conducted on 100% of the system or the product that it is you're looking at. As a rule, most things which have even a baseline level of complexity, we think about machines here, for example, will have or should be considered for a system FMEA, where the FMEA itself, the failure modes and effect analysis, focuses on the highest level analysis with a focus on system issues. I said focused a few times there, but the idea is that a system FMEA involves a bunch of people sitting down and saying, well, what can go wrong at the system level? And that question, that sort of baseline rhetorical question we're trying to answer, includes things like the customer or user experience, which of course includes the human machine interface. It importantly involves describing failure severity, which includes things like safety. So the system FMEA is really good at having all the people in the room come up with a really useful way of describing what bad and then even worse failures look like. And because we're looking at a system from at the system level, the system FMEA itself deals with interfaces between components and other systems. And a nice little number we like floating around in the reliability engineering world is that about 50% of all failures occur at interfaces. So one of the really easiest and fastest and cheapest ways to improve reliability is to focus on interfaces. A lot of the corrective actions for interface issues are negligibly trivial. And so you can really improve reliability greatly by looking at interfaces. Of course, you can always also ruin reliability by not looking at interfaces. A lot of organizations spend a lot of time and money looking at the components and nothing else. And all of a sudden, their final system or product doesn't work because one component does not interface well with another one. There's not much you can do about it when you release product into the wild. And of course, if you're dealing with sort of complex systems, you might have maintenance and support strategies that a system FMEA is really good at starting to come to terms with really early. There's more than that. System FMEAs are great at making sure we haven't missed any requirements or specifications. And beyond that, a system FMEA is there to prioritize effort and focus on the vital few. So you can see that a system FMEA gets done before we start designing. Once you've started designing, the system FMEA becomes less and less feasible. The idea is system FMEA prioritizes effort and focuses your reliability oxygen, so to speak, on the vital few weak points of your system. So that's the system FMEA. The design FMEA is conducted on some of the things that your system FMEA has identified as being problematic. So the things that are going to keep your team up at night when it comes to reliability, they're the ones that get subjected to design FMEAs. So we conduct design FMEAs on the high risk or vital few elements of the system that are going to potentially ruin your day. And you might find that there's 3 or 4 components of your overall system which are perhaps based on new or emerging technology or from a vendor you've never used before or being used in a brand new application. And so for whatever reason, your system FMEA said, these 3 components are the 3 components that we worry about the most. And so we're going to do design FMEAs on those vital few parts of our system that represent the high risk elements of said system. And we do that at the very start of design. Now, a lot of people I tell this to, the first response is, oh, well, what about the reliability of all the other stuff? Do we just not worry about it? And the answer is, of course, make sure reliability is baked into all the other components. It's just that the system FMEA decided that they represent such a lower, their risk of causing or being responsible for all the failures that this system is going to experience is that much lower than the high risk elements. All we need to do is just use good engineering judgment and good reliability engineering tools that don't need to be discerned from or identified as part of a potentially rigorous design FMEA process. And so the design FMEA gets done on the components that are going to keep you up at night, or the subsystem, with a focus on product design related issues. This is the medium in which we will identify those fast, simple, and usually free corrective actions to embed into the design. When I say free, of course, having thicker gauge wire is not technically free, but in terms of the overall concept or overall cost of making your thing like a smart lock, they are negligibly cheap. It should be costs that you would happily spend if you know that's going to make a more robust product in the end. And so the idea is that once we have these corrective actions, which include, for example, design changes, they can also include DFR tools. So, for example, if your design FMEA identifies that a PCB is something you are concerned about when it comes to reliability, you might, as a corrective action in your design FMEA, recommend that we conduct halt or sneak circuit analysis or whatever it is on that component which is keeping you up at night. Design FMEAs aren't going to always be able to bring a team together with predetermined answers for everything. So an entirely useful corrective action is to subject specific parts of your system to ongoing or future DFR activities like HALT, highly accelerated live testing. And for those who've never heard of HALT before, there's plenty of articles and podcasts and webinars on Ascendo reliability that deal with HALT. But if you've never heard of HALT before, it's just a test regime, essentially where you try to, in a scientific and controlled way, push parts of your system towards and then beyond their limits in order to find their weak points. And the idea, if you do this rapidly, those weak points can then very quickly be designed out of your system, and all of a sudden you now have a PCB or printable circuit board which is robust and not going to fall apart when that door is slammed multiple times. And so corrective actions can find those DFR tools. They can ideally, if you've never done any of this before, be embedded into your reliability plan. And so you have a strategy throughout the design process that a design FMEA can inform, which takes away much of the overwhelm. And again, we're only focusing on the vital few. If everything is important, then nothing is important. Then, of course, design FMEAs can be very useful for helping us develop system and component test plans. One of the many things we do when we design stuff is we simply or we forget about testing until it's sort of done, until we have to put together that document at the end of the production process. And then a lot of the times organizations just look at each other with dumb looks on their faces, where they go, all right, well, what does the standard say we need to test for? And then we have a bunch of potentially very expensive testing, which doesn't address the vital few weak points of your system. So once you know the vital few weak points of your system, you can then complete, as part of your corrective actions or schedule, tests that focus on those vital few weak points, because the design FMEA is all about the vital few dominant failure mechanisms. Once you have that, and once you're comfortable that the vital few dominant failure mechanisms on your list represent your system, then reliability decision-making becomes so much less stressful. When you want to model reliability, you only need to model those vital few failure mechanisms. You can then use things like accelerated live testing, which sounds like HALT, but it's not. That's where, for example, if you realize that your component or system is going to fail by fatigue one day, that's the dominant failure mechanism, And there will always be a dominant failure mechanism. You cannot design failure out of your system. It's going to fail one day. But if you know that when it does fail, it will be due to fatigue, then you can conduct accelerated life testing where perhaps you increase the stress or cycles to recreate 10 years worth of use into 1 week and get a really useful estimate on how long that thing will last. And that's what confidence looks like. We don't want to have to rely on test to failure statistics. That means we need to do a lot of testing to failure. And there's so many unknowns in how we test when we don't know what we're testing for, that often those tests don't represent how our thing is going to be used. So long story short, Design for me is their main focus is on improving the design. So the reason why they get done at the first start of the design process is because they have to influence the design process itself. Now, when it comes to design for me, is one of the most common mistakes I see is organizations often try to complete design for me is on everything. Doesn't work like that, because design for me are quite intensive processes. There's intensive activities. And if you don't listen to your system for me, essentially a system for me, which identifies all the trivial thousands of ways you'll think and fail as well, then you're doing design for me on absolutely every part of your product. Then what you tend to do very quickly is exhaust your designers and your technicians and your manufacturers. And when they become exhausted from doing design for me after design for me, they tend to go into robot mode where they just try to come up with corrective actions after corrective action, which might not be based on good judgment. They just need to say they've done one more for me before they go home that Friday. You don't want that. You want high quality FMEAs, design FMEAs, I should say, done on the vital few. You want to only use engineering judgment for low risk elements of your system. Otherwise, you trivialize the FMEA and everyone becomes exhausted by the process. And because of that, the FMEA doesn't make the design better. So FMEAs, where they are required to be done on every part of your product, often look like this, where you have one person furiously writing down all the stuff and everybody else is distracted, answering emails, tired, of course, on their phones. We don't want that. If you make your team do design for me and everything, good luck. Okay, so this system for me is there to identify the vital few parts of your system or products that need to be subjected to design FMEAs. Now, some of us might have heard of a software FMEA. Philosophically, a software FMEA is identical to a design FMEA in that it also focuses on subsystem or component levels, but instead with a focus on product coding related issues. So they're philosophically identical, but structurally and practically very different, because when we look at root causes of failure in the software world, technically every single one of them is a coding error that a software engineer made or didn't think that they needed to cover when they put those ones and zeros together at the very start. So the output of a software FMEA is high quality code. Perhaps where the software needs to, it involves fault-tolerant software, where the software is inherently designed to incorporate and incorporate things that are going to respond to flaws in the code as they become apparent. So, for example, you might have heard of what we call N-version programming. That means that we have perhaps 3 different programs designed and coded by different teams to do the same thing. Perhaps it's very important to multiply numbers together with a high degree of precision. We might get 3 different software engineering teams to come up with 3 different approaches. The reason being is that if there is a mistake in one, it's highly unlikely to be repeated in both the other programs. And so if 2 programs give the same output and one program is different, we can say with a high degree of confidence that the one program which gives the different output has a bug in it that's very specific to those inputs. And so we disregard that one and use the outputs from the two programs that agree with each other. And of course, you don't have to do that for everything, but for software where it's very critical that you get the right number, that could be a very useful approach. And the other thing we want when we code software is to make that code easy to fault find and debug. Any one of us who've been involved in writing code, whether it be for a product or maybe it's MATLAB or R or Python or what have you, we've all seen those coders out there where they just write equation after equation after equation without explaining what each variable means or what the equation is trying to do. And if they step away from their program for 2 or 3 months and then come back to this monstrosity of a code, they will have quickly forgotten what those equations mean, and they have to try and reverse engineer and work out what they are trying to do if they're trying to fault find and debug. And of course, that's 10 times worse if somebody else is coming in to try and improve the code. So the outcome of software FMEAs is to improve the code of the elements of a system, which are software. So let's just, for this conversation, have a software FMEA considered to be philosophically identical to a design FMEA, and we only do software FMEAs on parts of our system that a system FMEA has identified as high risk. But sometimes our item is really, really small or simple. It doesn't have tons of components or subsystems. It might be a very simple product that's going to be sold through Amazon or through some other marketplace. It doesn't have a lot of different moving parts. It might not be as complicated as our smart lock. So that means that we might not have a ton of high risk elements, or perhaps our staff have done this sort of design very, a lot. They're very skilled. They know what they're doing. Perhaps our thing is not developmental. It's just evolutionary. We're not trying to invent something brand new. Then it is okay in scenarios where, for whatever reason, you think we don't have to spend quite as much time and money on a FMEA, to combine them into one activity. The system and design FMEA is done at the same time. It's still a valid FMEA. It's still something that can be very, very useful, but for whatever reason, this is going to be an approach that some organizations use when they have simple items. It's not high risk, their staff is experienced, or it's not developmental, or it's a combination of all of the above. I can't tell you when it is and is not appropriate based on for every single scenario. The idea is that if it is simple enough, you might combine them all, the system and design FMEAs, into the same activity. System FMEA, so that this FMEA will involve the system considerations at the start, and the end of that activity will involve the same team once they've come back from lunch, going through design and software considerations. So that is how the system and design FMEAs interact. You have a system FMEA identifying the vital few parts of your system that need to be subjected to design and software FMEA. So before I move on, are there any questions about the system and design FMEAs at all, as I've covered them today? Cool. Now, before we move on and talk about process FMEAs, I need to talk about this thing called the criticality analysis. Now, there is a lot of wasted oxygen out there in terms of debates between different so-called experts on what is a FMEA, failure mode effect analysis, versus a failure mode effect and criticality analysis, or FMECA. Now, criticality analysis. What is a criticality analysis? Well, here's something that's not a lot of people really acknowledge, is that the criticality analysis has no genuine definition in the world of standards and textbooks in the world of FMEAs. Criticality analysis, for those of you who have heard of it, is simply one way of prioritizing the risk of each of different failures. The problem with that definition, though, and that's essentially a defendable definition in the world of FMEAs, is that in practice, especially in the world of defense and governmental customers, criticality analysis tends to be associated with an analysis of every single possible way your thing can fail, trivial thousands. And so criticality analysis in practice is an analysis done on every part of your system. Problem with that is that you cannot do it at the start of your design and build phases of your developmental lifecycle, because you haven't designed or built your system. So how do you know with absolute certainty how your thing is going to fail? How do you know you've covered all the failure mechanisms and failure modes? The reality is you can't. So in practice, what needs to happen, and there's no way around it, is that criticality analysis needs to be done separate to the FMEA as I've described it, system and design FMEA as I've described it, where we accumulate an understanding of failure modes and mechanisms during design and build. We essentially add them to the list and supplement our design FMEA outputs. And eventually, at the end of our design and build, we have worked out every possible way our thing can fail, and we've analyzed it to an extent, assigned a failure rate with it, and that then becomes, or is fed into what we call the criticality analysis for the entire system. Now, every failure mode has to be ranked using a combination of severity and other risk factors like likelihood. One of the problems with this is that you can only understand that once you've completed your design. And when I say that, that's not entirely true. There will be more failure modes and mechanisms that your customers and users will identify that you didn't know about every single time. And when we do a criticality analysis using the industry standard approach, so to speak, we associate a failure rate based on every single one of these failure mechanisms. And so criticality analyses can be useful when we're trying to predict the effects of failure. They're really useful when you're trying to put together a maintenance strategy or work out how many spare parts you need, or essentially design your logistics network or logistics capability. But what criticality analyses are terrible at, I should say, is improving your design. And so I've never seen an organization where they've tried to do a criticality analysis early have a good outcome. So we have system FMEAs, design and software FMEAs, and criticality analyses. And like I was alluding to just then, one of the biggest mistakes organizations who do FMEAs and conduct criticality analyses do is to try to complete the criticality analysis as part of a design FMEA. So all of a sudden, we have a system design FMEA and a criticality analysis where the organization desperately wants to get it all done and get it done in one hit. And that means that before we start designing, you have to have a failure rate estimate for every single failure mode and mechanism for something you haven't designed yet, which is which is fundamentally impossible. So FMEAs often turn into useless activities where we have massive spreadsheets full of a list of predicted or synthesized failure modes and mechanisms and have failure rates associated with them. And because so much effort is put into trying to create this spreadsheet of failure rates, we lose sight of what we're trying to achieve, and we don't get any good corrective actions. And many of the and when we do the FMEA, when we're forcing ourselves to come up with failure rates, then we look at all sorts of information sources to try and defend our estimates, ranging from parts count predictions through to OEM specifications and the like. But in practice, all these numbers are for somebody else's system and not the one you're going to design, not the one that you're going to come up with corrective actions for, or otherwise make amazing and awesome. So the FMEA report itself then becomes just simply a table of failure rates, and you forget to do all the other stuff because you're forced to try and come up with this farcical document early. And reliability suffers. We don't update it during design because so much effort was put in. Of course, we always miss unanticipated failure mechanisms because it was done very early. There's no prioritizing the vital few, Oh, excuse me. So it's generally a bad outcome when we are forced to do a FMEA very early. It just doesn't work. We go back to this scenario here. Okay, so that's the system FMEA, the design of software FMEA, and then the criticality analysis as nominally design-centric activities. But of course, all this is for nothing if you don't manufacture high-quality components. And so the manufacturing piece is where the process FMEA comes into play. Process FMEA, the process refers to the manufacturing process, but we've seen the process FMEA applied to all sorts of processes, including things like healthcare, also bureaucratic organization or very bureaucratic processes have been subjected to process FMEAs very successfully as well. But the overwhelming majority of subjects for which process FMEAs are mandated are manufacturing processes. And so a process FMEA in the world of reliability and quality focuses on manufacturing and assembly process analysis, focusing on manufacturing-related deficiencies. Now, we often look at a product having failed when it ceases to provide a function. So if we have a smart lock that can no longer lock or unlock, it has failed because that function has gone. A process FMEA for a smart lock actually isn't focusing on the smart lock itself. It's focusing on the machines and the people on the manufacturing line that work together to create the components that get put into the smart lock. And so when it comes to a process FMEA, failure occurs when a component is not what it's supposed to be. What is a component supposed to be? Well, the design FMEA is really good at helping us work out what the manufacturing specifications need to be for high criticality components or important components. And so those manufacturing specifications tell us when our manufacturing process has failed. If, for example, we are manufacturing a steel ball for a ball bearing, then a design FMEA might identify the limits on the diameter of that steel ball. And so if a process creates a steel ball outside of those limits, then our process has failed. So process FMEAs, failure is producing a defective component. Design, system, software FMEAs, and criticality analyses. Failure is all about the event where that product, where those components are put together within, fails in the hands of our user or customer. So a process FMEA is very important for making reliable things. There's no point designing something which is amazing and reliable if the manufacturing process comes up with defective components, which will cause failure very quickly. So the end goal is very, very similar, but process FMEAs are philosophically different, where the focus is the process and not the product. Of course, a product is there to inform the process, and a process FMEA will help you get high quality production going on. Process FMEAs are also really, really good at helping you get to high volume manufacturing very quickly. Process FMEAs aren't just about failure in terms of creating defective components. Process FMEAs are all about failure in terms of the process itself stopping or being otherwise offline. So process FMEAs are great at minimizing downtime, minimizing scrap and rework, and getting those high quality parts out there in a reliable product. You might have heard of statistical process control and process capability analysis. If there's something that you're interested in learning about, again, Ascendo's got a ton of resources, articles, podcasts, webinars about the both of them that allow you to take your manufacturing to the next level. Essentially, statistical process control is all about monitoring statistics of specific characteristics, such as the diameter of those steel balls. And what you're trying to do is identify trends, which might just simply be the precursors or warnings about your machines heading off in their own direction. Reality is every manufacturing machine starts heading off in its own direction as soon as it starts to be used, because it gets older, it wears out, or otherwise things change. And so statistical process control is all about giving us as much early warning about things starting to go awry so we can do things about that before we start creating defective components. Process capability analysis is all about measuring the extent to which a process will manufacture defective components. There's always going to be a finite chance that some components are defective, and process capability analysis is really good at working out what that number is. But you can only ever do PCA on a process which is what we call in control, where the machines are not wandering off doing their own thing. So you use statistical process control to make sure your machines are in control and not wandering off. And once you have confirmed that your machines are under control, then you can use process capability analysis to work out how many components you can expect to be defective. And really good processes have defective rates in the order of parts per million. So the process FMEA is different to the design FMEA in that the focus is improving the manufacturing process. And that's fundamentally what I'm going to talk about today, or already have talked about today. Of course, for those of you who have done FMEAs before, you know that there are things like worksheets and things like that. I'm not going to get into the details. I'm going to simply focus on a high-level difference between design and process FMEAs, and then talk about what that means moving forward. I can see that Carl has put in a definition of design FMEAs, or what they're supposed to do. And I agree with you to an extent, Carl, that they are there to prevent unnecessary product development issues. But that's not the only role of a design FMEA. It's obviously there to implement design changes. It's there to make sure that we design something usable. So one of the many things that design FMEAs can do is in Carl's comment and question. But if there's so many more things that design FMEAs do than just that. Okay, so a process FMEA focuses on a process. And what is a process? Process is a set of interrelated work activities that transforms inputs into outputs. And a manufacturing process is one of those processes that transforms raw materials or components into products. And high quality manufacturing means we limit how far important characteristics are spread out. Now, I'm going to introduce a trusty friend, or a trusty food type, bread, to those of you who have joined me for the first time. I often use a loaf of bread in my webinars and courses to talk about things that pertain to processes, because a loaf of bread is very universally understood, or baked products are very universally understood. We've all had bread before. We've all had cake, or things that are based on wheat and yeast and essentially fermented and then ultimately finished in an oven. But when it comes to these sorts of things, loaves of breads and cakes and the rest, there are lots of different things that help us identify whether something is high quality. The mass, the airiness, the amount of sponginess or the crust color, the number of slices of a loaf of bread, the thickness of the thinner slice. We all hate getting a loaf of bread from a store where we have a little slice at the end, which is 4 nanometers thick. It's practically useless. I know it annoys me. It probably annoys you guys as well. Perhaps the difference between the thinnest, biggest, and smallest slice is a big deal, especially if you're a parent who makes lunches for your children and you want to have each slice of bread roughly the same size to make sure you have some consistency with the amount of food that you provide your children at school. But of course, the baking process involves things like cost per loaf, scrap, defects, destructive testing. To test bread, we often have to test it in a destructive way. We get a randomly selected loaf and subject it to different things. And that means that loaf of bread can never be sold to a customer. Of course, we want our process to be efficient. We want it to be fast, have lots of loaves per hour. We want it to have a small carbon footprint, want to minimize environmental waste. All these different things are things that a good process FMEA can address. Now, many processes are represented with things like flow diagrams. And the flow diagram for this loaf of bread looks like this. Now, you can see here we have a diagram with lots of different shapes. I also want to highlight these different shapes represent different things. So you can see that things which are essentially mechanical are represented by a rectangle. Things which involve human steps represented with trapezoids. One of the first mistakes many organizations make is to forget about the humans in their flow diagram. Trouble with that is that humans are often the root cause of many process issues. So you really need to have your process well defined and well understood when it comes to a process FMEA. Now, process FMEA will look at each one of these little shapes and then subject them to an organized discussion to work out what might go wrong and try and come up with ways of preventing that thing from happening. And so this whole process and all the differences and all the randomness and all the different things that are going to combine essentially will be embedded in this random hand of manufacturing per se. Let's just call this the random hand of bread making, where this hand represents all those little changes from loaf to loaf to loaf that some of which we can never truly get out or eliminate or eradicate. That means that different bread will have different characteristics. And so if we focus on this characteristic we call chewability, we might create 100 loaves of bread, and each one of these loaves of bread will have a different chewability characteristic. And yes, chewability is a characteristic of baked goods. And you can see we have this bell curve behind these data points to sort of characterize the outputs of this manufacturing process. But of course, how do we know if our product has failed, our process has failed or not? It has failed whenever we produce a loaf of bread where the chewability is too low or too high. And so one of the many steps that's responsible for the chewability of bread is this machine here. Well, this is a machine, not a step, but the step that this machine represents. I want us all to focus on this machine and then think about it. Think about how it might affect the quality of our bread. Now, what this machine does is it takes a dough ball, which has already been mixed and rolled into a ball. That ball goes into the bottom of the machine, then goes along a conveyor, and it comes out the top right-hand corner of this machine, as you can see it. And so that dough ball, which combines yeast, carbohydrates, water, and it took some time and temperature to get there. And once it's in what we call the intermediate proofer, the idea is that this intermediate proofer is there to add temperature over time to promote fermentation. Now, fermentation is essentially where the yeast, the organisms within our dough ball, start having a party, and they take sugars and carbohydrates, and one of their outputs, or one of their byproducts, I should say, is gas bubbles, CO2 bubbles. And those CO2 bubbles are very important because those CO2 bubbles are the things that create that spongy texture in our baked goods. And now that we are going to do some more fermentation later on in the process, but the point behind this intermediate proofer is that it provides or starts the fermentation process just enough to get a dough ball which is just a little bit bigger, and the gluten is now a little bit more relaxed, and it allows it to be molded. It allows it to be rolled into a long shape that will eventually allow our loaf of bread to be created. So, of course, our intermediate proofer has a temperature setting. And what we want to do is we want to make sure that temperature is not too hot and not too cold. If it's above 29.4 degrees Celsius, then the dough essentially loses too much water becomes too solid and can't hold the gas bubbles. If it's below 26.7 degrees Celsius, there's not enough heat for the yeast to do its stuff. So the yeast can't create enough bubbles. So we want to have our temperature right in the middle of that range. And not only that, we want to have our dough ball within our intermediate proof of anywhere between 5 to 15 minutes to get the right amount of gas bubbles. But of course, the real world is frustratingly uncontrollable to an extent. And even though we might have a temperature gauge in this machine, the actual temperature within different parts of this machine might be different. So what I want us to do right now is, I'll come back to your questions in a minute, Carl, but I want us to look at this intermediate proofer. And if we don't get the time and temperature right for our dough ball, we will have a loaf of bread which doesn't hold shape, which isn't spongy, and is otherwise not chewable. So a process FMEA team will sit down and look at this machine or look at this step and say, what could go wrong? What might failure look like? So what we're going to do right now is we're going to brainstorm as a team some potential corrective actions to ensure our process doesn't fail. So we'll go back to the picture of our intermediate proofer. I want people to think about what could go wrong and what can we do to make sure that those things don't happen. And once you've got an idea, feel free to share it in the chat window. Anyone want to brainstorm about what could go wrong, having described multiple? Okay, so Mark said that we might have multiple temperature monitoring points. Mike mentioned that the heat element fails in some way, so the loaf could move too fast. Awesome. This is fantastic brainstorming. What happens if, is it possible for our dough to not be heated in a uniform way? The conveyor fails. Love it. Anything else? What can we do? And when we say conveyor fails, Mike, of course, conveyor failure can mean anything from it ceases to work entirely through to it moves too slowly, or it doesn't go through the right way, or is the dough rotated during its passage? Fantastic. So this is a sort of brainstorm. Temperature gradients within proofer. The dough is too small, too big. Right. Okay. This is brilliant. Absolutely brilliant. And so we're some dough buildup could collect inside the machine and change the rate of transit. This is what a process FMEA is all about. Inconsistent shape of dough. So fantastic. We know that a spherical shape will have a certain heat profile without the dough, but if it's anything besides spherical, then the extreme points or pointy bits of that dough will get heated in usually a much faster way. Machine fails to notify the operator if there is a problem. And so the process for maintenance issues due to machine age, love it. And so the corrective actions that we come up with include, and some of us have already come up with a couple, multiple temperature monitoring points. Mark came up with at the very start. So where we might do some sort of initial manufacturing testing or baking testing, work out what the optimal temperature distribution is, have those monitoring points in our intermediate proofer, write down what they are, and those temperatures change markedly during our subsequent baking operations, we know we've got a problem before it becomes a problem. Maintenance issues. So one of the corrective actions might be is that we look at our preventive maintenance and make sure temperature sensors are cleared or tested or what have you. We might ask the team behind the manufacturer of an intermediate proofer to have multiple or redundant sensors to make sure that if one fails, the whole process isn't ruined. If the temperature fails, determine what happened to that dough. So if you see that, I'm guessing, Mike, you were saying that if the temperature is not doing what it's supposed to according to what our sensors say, we then have a process in place where we take that dough and examine it to see what's going on. Fantastic. And so, as you can imagine, one of the reasons why I use the intermediate proofer is that the problems associated with poor fermentation often won't become apparent until the loaf of bread has been fully baked. We don't want to have to wait till then. If we know how our intermediate proofer is supposed to behave, and if we have already worked out that perhaps we need to make sure the temperature gradients are right, we need to monitor conveyor speed, we need to make sure the dough ball is a consistent size, so we might add a step where the dough ball is, the dimensions are somehow checked beforehand. Now we're coming up with fantastic corrective actions. And the reality is adding temperature sensors in an intermediate proofer does involve some cost, but that's a pretty small price to pay compared to even an hour of downtime or a week's worth of recalls of loaves of bread. And so that is the inherent difference between a process and a design FMEA. The process FMEA is looking at how we can change the process or what corrective actions we can implement in our process to make sure that whatever it is our design FMEA says we need to build is within specifications, i.e. not defective. And if you have been able to see that these are some really useful corrective actions for this baking process, then congratulations, you fundamentally understand what a process FMEA is all about. One thing I will say is that we don't want to have just throwaway statements. So, for example, we don't want to have as a corrective action investigate or implement preventive maintenance. That's just too high level, too broad, too easy to satisfy without ensuring we're addressing the main issue. Preventive maintenance could be simply something be as simple as wiping down the exterior of a machine. If you're going to say we need to have preventive maintenance, specify what that preventive maintenance is supposed to achieve. If the preventive maintenance is there to make sure that the temperature sensors are working and are calibrated and are free of dust, free of dough, free of crumbs, etc., 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 write that down. Don't just say do something at very high level without thinking about it. Be as specific as possible, because when you're as specific as possible, it gives tremendous guidance to the people who are going to implement that corrective action, and more often than not will actually address the issue. If you just have a corrective action which is do preventive maintenance, good luck with that. Of course, preventive maintenance is always important, or sorry, it can be important for certain machines, but you need to give your team a hand and not just fill up a spreadsheet full of throwaway statements. Okay, so Carl's asked a few questions. I believe there's three questions Carl is expecting answers for me from. Carl writes, unfortunately, it's sometimes possible to do everything right, but at the wrong time. How does one perform FMEA at the wrong time? I don't think about FMEA until something goes wrong. Any thoughts? Yes, FMEAs are often done at the wrong time. And in my opinion, the root cause of those FMEAs being done at the wrong time is that culturally, the organization does not understand FMEAs or is not motivated to conduct them. Organizations that simply want to say they've done a FMEA and nothing else are the ones that tend to do it at the wrong time. Organizations that love FMEAs, and there are plenty of them out there, plenty of organizations use essentially nothing but FMEAs to provide their strategy for reliability. They know that the FMEAs are there to provide corrective actions. So they inherently know that they need to do FMEAs at a point in time where those corrective actions are easy to implement, i.e. as early as possible. And you don't want to do it too early, because a design FMEA done on something that you have not got a good idea about the design for is often a waste of time. So you need to get the balance right, but 9 times out of 10, FMEAs are done too late by organizations who simply want to say that they have done a FMEA without valuing the outputs of a FMEA. Carl then writes, how can fault tree analysis and event tree analysis help in a FMEA? Okay, so fault tree analysis is, I've done a webinar on fault trees if people are interested and never heard of them. A fault tree is used in one of 2 scenarios. One, to model system reliability, where you try to work out how reliabilities of components combine to create system reliability characteristics. And the second time fault trees are used is for root cause analysis. Now, root cause analysis sounds terribly retrospective, but root cause analysis is often done in a predictive way, including in FMEAs, where you try and predict the likely ways your thing can fail. And a fault tree is very useful to do that. Now, many organizations don't do FMEAs. They use fault trees in a very similar way to try and predict how their thing will fail to develop corrective actions. So fault trees and FMEAs are often used in, I'll say, competing ways, but there's not, in some organizations that just prefer fault trees to FMEAs. Some organizations prefer FMEAs to fault trees. Fault trees tend to be less prescriptive in their steps, but a good fault tree analysis is often just as good as a good FMEA. And in a FMEA itself, you will often, when you're struggling to identify root causes of potential failure modes and failure mechanisms, a fault tree analysis, little one, can be conducted as part of the FMEA. So, for example, in our process FMEA, we might use fault tree analysis to try and work out what could go wrong with our intermediate proofer. And so that fault tree analysis then comes up with potential root causes, and then those root causes then are used for us to help brainstorm corrective actions, and those corrective actions then get put into our FMEA outputs. The reality is, everyone tends to have a preference for certain tools to be used in certain scenarios. I've seen FMEAs and fault trees used equally well and equally valuably in similar scenarios. Sometimes FMEAs are better. Sometimes fault tree analyses are more relevant, and sometimes FMEAs include fault tree analyses. But if you want to learn more about fault tree analyses, please feel free to look at the webinar we've done in the past. Now, event tree analysis is specifically used for scenarios where time matters, i.e. the sequence of events matters. Fault tree analysis tends to be rather static, i.e. any combination of events will cause certain things to fail. Event tree analysis looks at the sequence of events, and that's particularly useful when you involve humans. So, for example, warning light goes off. Does the human observe the warning light? Yes, no. If the answer is yes, does the human do the right thing? Yes, no, etc., etc., etc. So event trees are very useful for scenarios where the sequence of events matters. However, I haven't seen event trees used a hell of a lot in FMEAs. That's not to say they don't have a place. If you are looking at human-machine interfaces in particular, event tree analysis can be very useful. But hopefully that answers your question, or gives you enough material for you to go ponder the conundrum that gave rise to that question. And last but not least, Carl asks, how do I create generic FMEAs for a family of products? Well, the first thing I'd say is be very careful with defining generic FMEAs. The reason why you need to be very careful is that when you have generic FMEAs for a family of products, it often means that people with a generic FMEA for a product that's about to be developed put their brain in neutral. Why? Because the FMEA has already been done. So generic FMEAs do have a place, but there is a high risk associated with them. And that is that we stop thinking about new and emerging problems because the FMEA has already been done. Now, there's plenty of organizations which use generic FMEAs very well. Don't want to say that's not a thing, but they understand their place. And in many cases, these so-called generic FMEAs are essentially kernels of thought, or the initiating product for a broader FMEA, where the team then investigates all the things that have changed for a particular product, all the things that are new, or all the things that are relevant to this product being used in a new environment. So hopefully that answers that question as well. Okay, so we are almost at the end of our window for today. If there's any more questions or comments, please feel free to share them now. I'll hang around as long as it takes to answer them. But if people need to disappear because I'm not sure what time it is in the Netherlands, but I dare say you might have things to do. Thank you very much for joining us today. If you have any comments, thank you, Mike, and thank you, Carl. If you have any comments, any ideas, any questions that you can't fit into this conversation, please feel free to put them in the comments window at ascendoreliability.com. And also, if you have any ideas for future webinars and podcasts, please let us know. Fred and I love talking about reliability as much as the next person, but there comes a risk that we just focus on the things that are our favorite things and not the things that are the most relevant things. So please feel free to tell us what we need to talk about in the future. But in summary, it seems like you guys already know what a process FMEA is because you came up with some wonderful corrective actions for our process that weren't just machine-centric. Thank you, Sebastian, as well. Thank you very much for that feedback. Much appreciated. Again, if there's anything else, please feel free to reach out. Thank you. Remember that in society, the upper crust is a bunch of crumbs held together by a lot of dough. That's right. If that's the main takeaway, I'm happy with that one as well. Now, so Sarah asked, do I know anything about the FMEA MSR when it's used? And that FMEA MSR is often used in the world of functional safety. Now, functional safety is a really interesting thing. Thanks, Max. It's a really interesting thing to define. And potentially that is the subject of a whole new podcast. So functional safety is, what's the best way of talking about functional safety? Or it means that the system has inbuilt functions where the functions themselves are there to make things happen as well and that keep your system safe. Perhaps an example is a laser cutting machine, which has its own functions that identify when an operator is drowsy or not doing what needs to happen, and perhaps automatically shuts down the machine as well. Another one is eye tracking in vehicles, where vehicles are able to identify when people are focusing on a mobile phone or cell phone as opposed to the road ahead, and then maybe can do something about it. So MSR stands for monitoring and system response, which is sort of a broad term for that sort of stuff. And if I'm going to be honest, I think FMEAs have a really useful role to play. They are considered their own type of FMEA, especially in the world of vehicles and driving. And I think that what tends to happen with MSRs is that the MSR piece, the monitoring and system response, becomes so much of the focus that we forget that we're there to find those basic corrective actions. And so we can have corrective actions which are simple, fast, and free, sort of omitted, because we feel like we need to have some sort of device or component or machine or sensor which is going to, in a very proactive way, step in and save the day. So I definitely think for me, as with monitoring the system responses as part of the whole functional safety piece, they can be extraordinarily useful. The risk is that we focus on having really sophisticated solutions to basic problems. Does that come anywhere close to answering your question, Sarah? No worries. Okay, Fred, it seems like our participants are dropping like breadcrumbs off the baking table. Thank you for your feedback. Thanks, Kenneth.